Scusami. Grazie, grazie. And they don't have confinement on the, so there is no clear one-to-one relationship between the two things. It may be arguable that if you have confinement, you need to have a symmetry breaking, but that's not even sure. So this is again an interesting question. And there is also a more modest but very interesting question in which we ask whether we can then uncover some phase transition, maybe with some strange unknown order parameters. So maybe there is something in a system and the system change state and there is some order parameter that we haven't quite guessed. And that's something I will say a few words later. Ma aiuto Maria. Aspetta. No. So. Yes. I can use this one, no problem.
No, it should work.
It should work again. Yes. Oh, fantastic. Wow, I am impressed. So then just to make a very small comment on the theory side of these things and how you approach these issues and which is the natural playground to discuss this. So we were really playing, I made a phase diagram, a cartoon, and I used the temperature and the number of light flavors in this cartoon. And so for 0 light flavors, we have this Yang-Mills theory that we have been studying in the paper that we are discussing now, and also the finite temperature Yang-Mills theory, but Giorgio and was studying when doing this the confinement transition. This is a wonderful playground for string models, of course, so you can really rewrite this Yang-Mills theory as a theory of strings, and you can play with this theory to study non-equilibrium. This is important theoretical setup, both in the symmetric and also supersymmetric world. And really, I don't even try to summarize what has been done here. Is absurd. When I start increasing the number of flavor and I have, say, 2 light flavors, this is more or less our world. They should be a little bit massive, but this is what we have. So we are sitting along the blue lines rather close to 0 for 2 light flavors, 2 to 3 light flavors, where we treat the theory in chiral perturbation theory. So that's where we are. Very interestingly, when NF becomes quite large, QCD doesn't break chiral symmetry anymore, and we enter in a conformal theory, and we enter in this conformal theory via a quantum phase transition, 0 temperature quantum phase transition associated with essential singularity, similar to Kosterlitz-Sauer's transition probably, but we don't know for sure. All these other little dots that I made, they should be genuine phase transition, and they should be regulated by a 3-dimensional theory. When I study thermal phase transition, as we did in this paper of the Yang-Mills for the first time, and we exploited this problem, it's important to remember when we have a thermal phase transition, we have diverging correlation length, we are in a box, we can make mode expansion of our bosonic system, but since we are at the diverging correlation length point, all the modes, massive modes, would decouple, and only 1 0 frequency mode would survive. So when we study these theories, these are 3-dimensional theories described by 1 single bosonic degrees of freedom, and we study with universality. But then we hit this conformal phase transition at 0 temperature, which is all different, it's a quantum phase transition. I find this interplay very nice and fascinating, and we still don't know many things. By the way, it may, one important application of more contemporary theoretical studies is this discovery of the anti-de Sitter conformal field theory correspondence in the strongly coupled quark-gluon plasma, which is even experimentally verified. One logic behind that could be the connection between this strongly coupled region with the strongly coupled conformal theory at 0 temperature. So this is all interesting. Many people are debating this. There will be a nice workshop in Prague in the next months where we will try to make sense of this. But what I find curious is that this thing is quite general. I think if I would draw, for instance, like a spin glass in the temperature external magnetic field, I may draw something quite similar. with the second order thermal transition eventually giving way to quantum transition. So that's something to play with, and probably one of these fields where lots of communication can be very interesting among different communities. And computers, next, very important legacy of this early paper. Maybe you have heard this lovely seminar by Arianna that was here at the Sapienza. And Arianna started off as a lattice physicist, but now she's a philosopher and historian. And so she has a very deep perspective. And what she points out, I think, something important. And again, why it was so transformative, this paper and these early days of lattice field theory, because computational physics came of age. I mean, physicists have always used computers, but then it is different saying, okay, I need to compute these little things and I write my code and I compute, or use computers as a support to a more general research framework. It's interesting because we ask questions which are the questions of theoretical physics, but in a sense we do experiments because we measure things with errors, and then we have to put this together with the theory. I think Arianna was discussing this very nicely, and I think culturally this really made a difference. I remember also, but to be more specific, why I remember this sentence, and I don't know, Enzo, if you can remember, I think someone said this at the Fermilab conference, where Ape was presenting the first results. And I remember someone giving the talk, and not one of us, of course, but someone else by friendly competitors, and say, Ape sets a new standard, because it was really, as we see also from the slides by Giorgio at the beginning, was really a huge jump. And then, of course, many others were followed, but I think they were at the same, starting more or less at the same time, a tight race, friendly competition. This is the Columbia project. And then probably the most recent interesting thing is this Janus project, which is really devoted to spin glasses. It's not super powerful, but very super concentrated on this physics. I was telling at lunch, George, I copied this. I don't understand this paper, but I like this connection between aging and rejuvenation. I find very appealing, and I would like to learn something about that. And then finally, this is what happens is that really we made such an impact on commercial environment. Many lattice physicists went to IBM. That was super impactful indeed for us. But one important imprinting that I really like to discuss, to point out, to bring to your attention, it comes to the application to artificial intelligence. So now lattice people are entering very aggressively the artificial intelligence game. And there are groups, I think in the United States at MIT, and there are this snowmass has been done both from MIT and European friends, but I think really driving force is mostly at MIT and UK. And they feel really, I realized by talking to them that they really feel empowered by this early success. They say, we know that we lattice physicists can be really very, very good at doing this because we have already done. The community is so strong and the community will make the most. So this is really the logic of what we can debate whether the analogy holds. That's an interesting question to discuss. Actually, it was a discussion, part of the discussion 2 weeks ago was a workshop in Munich on machine learning, where we were really discussing perspectives and impact and whatnot. But certainly, those of us who are really seriously doing this are inspired, again, inspired by this impact on computational physics that lattice people did in past years until now. I cannot resist then telling you something about machine learning because again, Polyakov loop comes again into play. That's very strange and weird observable in many respects. So that's a very basic, nice, it's a basic Nature paper of 5 years ago where they, at the beginning, they started up as a warm-up studying easy model with machine learning, supervised and unsupervised techniques. So far, so good. But then they became more ambitious and already super interesting because they studied a model without local order parameter. So you look at this configuration, it's not so clear to guess which is which. And then get their machine learning algorithm, you should read the paper, it's rather technical, but clearly written. And they were really able to classify configurations. And what mathematically distinguished them is the behavior of the 2-point correlation function, the same correlation functions we were studying for the glueballs, but then depending on the phase, the long time decay is different, and this is what classifies the phase. Amazingly, the algorithm managed to identify this. One can play with the Polyakov loop. Once you define the Polyakov loop, you have basically a cube of spins. You have created this Polyakov loop, so you have a cube of spins, and you can try to classify, I won't enter into this, to classify the phase by analyzing the Polyakov loop. That works, but it's also a bit trivial. But what is really interesting in the machine learning setup, in a machine learning setup, is this work already over 4 years ago, about by Betzel and collaborators, because they started with a simple, even simpler version of Yang-Mills theory with only 2 colors. And they were analyzing configurations, gauge configurations, always the same, of these 2 colors. But they weren't building the Polyakov loop. They were just giving these complicated collections of gauge fields to the algorithm. And amazingly, the algorithm not only did identify the different phases, that's okay, quite something, but also computed. It did compute. It recognized the order parameter. So the function that decision function, which is the characterizing element of any machine learning algorithm, so the object that you use to say which is which, was decided by the algorithm, and this decision function, so the quantity that you should look at, is indeed the Polyakov loop. So that really makes lots of suggestion that you can use these techniques to explore phases that you don't know. Maybe you uncover confinement, maybe you learn about axial restoration, and many other things that would be too boring to discuss now. But then I want to finish with smearing. That is really last but not the least. What happened to smearing? This initial apparently simple idea, are we still smearing? Yes, we do, enthusiastically and everywhere. And for instance, everyone is still analyzing this. These are 2 among the strongest players in the field. And very recently, they wrote a paper and they say that still the most used smearing in the field is the upper smearing. And they say, oh, we want to improve a little bit. In which sense? Well, maybe you already forgot now because I said at the beginning, but we started by smoothing up SU3 matrices. And then, of course, you add up SU3 matrices, you go out of the group when you do this. So you need a procedure to project back on your group. So and in our old times, that was done, well, let's do it in some way. And it worked very beautifully. But they decided they want to do it more theoretically, more systematically. Did, formally very nice, but results very much the same. Probably the most interesting evolution, and I think, Julia, you are expert probably on this, is this Lusher gradient flow, in which you again design a smoothing procedure which brings you closer to the continuum limit. This is what smearing is supposed to do. It's formally super elegant, very well argumented. It really convince you that you can't be wrong by doing this. But in a nutshell, you are really flowing, you are smoothing the field using a flow time, similarly to smearing. And eventually, what happens after the flow, that you have smeared over a sphere. So there are similarities. People are analyzing different smearing, for instance, and many studies have been done comparing because of course it's so simple and so clean, this idea of smearing, that it's very tempting to say, okay, but now I focus and try to do better, but it's never really better. I don't know, I really hear other opinions, experts may have other opinions, but clearly anything you imagine can certainly be reformulated as a smearing, just because the idea is so simple and so general and so close to the general concepts of renormalization group that it's difficult, I think, to do something which is conceptually different. And these papers in different points of view are all going in the same direction. And this is the most systematic, really done it systematically by the ETMC collaboration. They were attacking one of the problems which really require lots of attentions in controlling local fluctuations, because when you study topology on the lattice, well, I think Giorgio has been the first one to explain me a little bit of topology on the lattice, but now I was trying to remember, he was using cheese. You made some explanation using some cheese, but I mean, that just to explain how the field can become complicated and tangled. But I mean, what happens clearly that topological, so what is topology? Topology is something which is resilient under small deformation. And then you clearly imagine that if you discretize and if you cut, topology is the first to go, because when you have a Möbius strip and I cut, then where is the Möbius strip anymore? So we can imagine that it's really very difficult and is a very severe test bed for topology. So for smearing. So you really need this smoothing procedure to study topology. This is very systematically done by our friends of the extended twisted mass collaboration in Rome, in Berlin, and in many other places in Europe and elsewhere. And you don't need to read, but this long list here is a list of all the techniques that you may use to measure the topological susceptibility on the lattice and the level of correlation between them. All of them, those who rely on gluonic methods for the study of susceptibility, have to rely on smearing, and they do rely on smearing. And then you see that the upper smearing is still very strong contendant, so it works as well, absolutely, as or more precisely, the other methods work as well as the upper smearing. That's no longer true. That's I leave you under my last slide with a puzzle. Because indeed, when topology is studied at high temperature, we still don't know how to bring things together. So maybe we would need some new smearing techniques, or maybe coming back to the first question, maybe we are not really asking the right questions and we should rethink. That's something time will tell. But now I think I then show again my summary. And I think that after more than 30 years, I think the summary is really justified. This beautiful paper set a couple of milestones. And these tools that were introduced, they were really there to stay, and they have really produced a number of inspiring and important results. And so with that, so thank you very much again. It's been nice. Thanks.
Thank you very much. It was very nice, very interesting. We open for questions. Maybe Giorgio, you want to say something first?
No,
or
don't have to. We can go for coffee, probably.
Maybe. If you want to come here, maybe on the.
Now I feel embarrassed.
Okay.
Okay, so thank you, Maria Paola, for this wonderful conference that caused me very important memories, memories also of friends which unfortunately disappeared. But anyhow, so thank you. It was a wonderful time. And thank you also for you for all the time that we were together. Now, let me would like just to comment about the machine learning. One question that I'm thinking about machine learning, maybe people already thought about this problem, but it's the following. Suppose that you do a numerical experiment in which you produce something, for example, I think of the two-dimensional model. You produce, you take the size 20 and you produce a configuration of the two-dimensional IC model. Now you have the computer, the machine, what you want to learn this type of configuration, which is something that you have discussed in some way. And now you ask it to produce configuration of a 40, size 40. I mean, it's something, because this is something that could be interesting in some field, because sometimes you can do, well, we all know very well that, for example, in lattice gate theory, we can do only small lattice, not, well, now I'm much bigger.
No, sure.
But anyhow, they always, you would like also to have something bigger. And now my question, if in some sense one could not use machine learning to produce the result for larger lattice, having learned something for small lattice. Of course, you have to cook some kind of algorithm for doing that, but with, I mean, cookings are putting together some idea that you know of what happens is statistical mechanics with machine learning.
Well, that's, first of all, thank you very much, Giorgio, for your kind words. And well, as usual, you are absolutely ahead of everyone. So it's something that it is done, it is there, but it is not so completely appreciated. And it happens somehow as a byproduct of some other effort. But maybe then what you say, since you say so, then it should become more important. Let me explain. There are, especially these friends at MIT, the Fiala, Shanahan, and Will Detmold especially, they are really working, and probably those who are still in lattice know Fiala very well. She's fantastic, absolutely. She's a driving force. And they are, they started with this. We want to accelerate algorithms that probably Enzo has been following. I don't know this part. And then they have some trick basically to coarse grain the configuration. You evolve in the coarse grain. And then with machine learning, you do a pattern recognition so that you reverse engineering what you have done and go back to the original configuration. Now, as a corollary of considered so far byproduct of this, indeed, you can make a machine learning assisted reweighting also in volume. So this is the idea that, you know, once, because if you have this technique that you go from large lattice, you coarse grain to the small lattice, and you know how to go back to large lattice, but then you say, why don't I just start with small, what you say, why don't I just start with small lattice and I jump to the large lattice? And yes, they do this. And what, because we were really discussing whether it's really worth to use machine learning to speed up configuration generation, because you say you have to work so hard, but it is really worthwhile. And what the people who are really expert on this side of the problem, they say, yes, it is, because what you have to appreciate is not just the speed up of generating this particular set, but the possibility of using this set to extrapolate to different volumes, to different parameters, think of different temperatures, because of course, when you change the volume, you can also change the temperature, to different couplings, to different masses, if you want to study the chiral regime in QCD. So I really, yes, you touched, I think, the most important point. Yes, and I think the communities is heading in that direction. They should be encouraged to do so. But probably indeed, spin models could be a better starting point, because you may have all the proper idea. Yeah, I'm looking at Massimo because I think it may be someone really cooking up something there. That would be really great. Yeah, that would be really great, because, you know, if you have a simulation and then you can cover it all, and that would be, yeah, thank you.
Thank you. Other questions?
Coffee.
Comments? We have some time. On that side, I move here, so I it was so clear and so complete.
There is no match. I mean, it was just memories.
Yeah, more than a question, is a sort of
yes,
comment. I think it was a really nice environment where to work, and I had the luck, as you tell, that I had my thesis work in this paper, and a particular aspect was that you had to develop something new. We had a new platform, new hardware, new software, and you had to test those tools. And in some sense, you use the physics result to test the software that you were developing to study new physics.
Exactly.
So it was really a nice sort of feedback mechanism that was very peculiar.
Absolutely,
And
yes.
It was an incredible lesson for me under the guidance of Enzo, of course, or Giorgio, to develop the software in this strange environment with a new programming language, using new software and numerical techniques. And you made a very excellent review of this work. Thank you.
Thank you very much. I really want to then follow up again on these comments by Arianna, because really it had to be appreciated that it was a different way of doing science, in a sense. It was quite new and quite interesting. And yes, well, there are many recollections from those times, but indeed there was the sense of a transformation, which is good. So thank you very much again to all those who were there, those who are no longer here again. So, shall we?
Do you have any other question or comment or recollection or something?
Thank you.
If not, we can thank Paola again.
Thank you very much. Thank you.
We have the coffee break outside and we reconvene at 4 p.m. for Enzo's talk.